Michaela. Have you ever wondered, how our ear works? How do we hear?
I don't know. I've always been really curious about it. We should find out.
We should. Let's do it.
Here we have the outer ear, also known as the auricle or the pinna. The outer ear helps channel sound waves and directs them towards the auditory canal. It also improves the sensitivity to high-frequency sounds around 3000 Hz. The outer ear is made up of several depression and prominences. Here we have the helix, the antihelix, and the intertragal notch, just to name a few. As sound waves make their way towards the middle ear, they travel through the external auditory meatus or the external auditory canal. This area is commonly referred to as the EAM or the EAC. The lateral one-third of the EAM is called the cartilaginous portion. The cartilaginous portion contains the sebaceous glands that produce cerumen, or what is commonly referred to as earwax. Earwax is actually quite useful as it protects the ear from bugs and dirt and warms the air as it makes its way through the EAM towards the tympanic membrane. The medial two-thirds of the EAM is called the bony portion. There are mastoid air cells within the temporal bone, which is a section of the skull that encases the bony portion of the EAM. At the very end of the external auditory meatus, you can find a disc-like structure known as the tympanic membrane, or more commonly referred to as the eardrum. The tympanic membrane acts as a gateway to the middle ear.
Once sound waves have traveled down our external auditory meatus, they then hit this gateway to the middle ear, or our tympanic membrane. Once they hit the tympanic membrane, it begins to vibrate, and these vibrations begin to rock the ossicles of the middle ear, which is how sound gets transferred from the outer ear to our middle ear. Now let's talk about the three ossicles that lie within the middle ear. These also happen to be the smallest bones in our body. The first of the three ossicles is the malleus. The malleus is embedded on the medial side of the tympanic membrane. The malleus then connects to the middle bone of our ossicle system, known as the incus. From there, the incus connects to the stapes. The stapes is the final bone in our little ossicle system, and it rests against the oval window on the medial wall of the middle ear. This point serves as the connection between the middle and inner ear. The function of the middle ear is to assist in transferring the acoustical energy from the outer ear into mechanical energy in the middle ear, which can then be transferred to the fluid-filled inner ear. This transfer of energy works through the movement of the ossicles. When the sound wave hits the tympanic membrane and it vibrates, as I previously mentioned, the vibrations of the tympanic membrane cause the malleus to move back and forth. Once the malleus begins to move, it sets off movement in the other two ossicles through lever action. In addition to the transfer of energy from acoustical to mechanical, the middle ear also functions as an impedance matching system. This means that our middle ear actively makes up for the loss of energy that would occur during these energy transfers from acoustical to mechanical energy if we didn't have the middle ear system. As I said earlier, the stapes rests on the oval window of the medial wall in the middle ear. This is the gateway to the inner ear, which we will now move on to talking about.
The inner ear contains two important portions that we are going to focus on: the cochlea, which is the organ for hearing, and the vestibular system, which helps with the balance and field of vision. For now, we'll focus on the cochlea, which is located in the petrous portion of the temporal bone. The cochlea, which is connected to the middle ear by the oval window, makes about 2.5 turns and contains three different canals: the scala vestibuli, the scala tympani, and the scala media, which is also known as the cochlear duct. The scala vestibuli and the scala tympani are both bony canals that contain fluid known as perilymph. This perilymph fluid is rich in sodium and is comparable to cerebrospinal fluid. The cochlear duct is a membranous canal that runs between the scala vestibuli and the scala tympani, and this contains endolymph fluid. The stapes pushes on the oval window, which moves the perilymph of the scala vestibuli up towards the apex of the cochlea, also known as the helicotrema, and then down through the scala tympani. The pressure from this movement of fluid causes displacement on the round window of the medial wall of the middle ear. The cochlear duct is separated from the scala vestibuli by Resner's membrane and separated from the scala tympani by the basilar membrane. The supporting shell for the basilar membrane is known as the spiral lamina. Within the cochlear duct there is a very important structure called the organ of Corti. This is the end organ for hearing in the cochlea. The organ of Corti, which rests on the basilar membrane, senses the acoustical information that is being sent from the middle ear. It contains outer hair cells, which are sensory cells that line the basilar membrane in 3 to 5 rows. There are roughly 12,000 outer hair cells in the entire cochlea. There are also about 3,500 inner hair cells that line the basilar membrane in just one row. The cilia of the outer hair cells are embedded in the gelatinous membrane known as the tectoral membrane. The inner hair cells, however, simply brush against this membrane. The mechanical energy from the middle ear shifts the perilymph within the bony canals, causing the Resner's membrane to shift the endolymph in the cochlear duct. This movement then moves through this canal to the basilar membrane, causing the hair cells to move. As the cilia on the hair cells bend, there is a chemical-mechanical cochlear microphonic release, and this information is then sent along the spiral ganglion and down the auditory nerve to the brain.
Next, we'll talk about the other important portion of our inner ear, the vestibular system. The vestibular system uses the fluids and organs of our inner ear to help us orientate ourselves in the world around us and maintain balance. The vestibular system is made up of a utricle saccular system and the semicircular canals. The utricle saccular system is made up of 2 membranous sacs that sit within the vestibule and are filled with endolymph. There is the utricle, which is orientated on the horizontal plane, and the saccule, which is orientated along the vertical plane. The maculae are what we call the end sense organ that lies within both the utricle and the saccule, and these sense organs are used to sense gravity and linear acceleration of our body. Specifically, the utricle detects horizontal acceleration, like walking backwards or forwards, or the movement of a car when a car first begins to move. Meanwhile, the saccule detects vertical acceleration, like when you get in an elevator and it goes up or down suddenly. Beyond the utricle and saccule lie the semicircular canals. These are bony canals with membranous canals running through them that are responsible for angular acceleration. There are 3 semicircular canals: the superior canal, the posterior canal, and the horizontal canal. The superior canal is stimulated when we shake our head, yes. The horizontal canal is stimulated when we shake our head, no. Finally, the posterior canal is stimulated when the head moves to indicate a sort of maybe movement.
Wow! The auditory pathway is really fascinating.
Yeah, it really is. It's really interesting how much work it goes through just to get sound from the outer ear into the inner ear.
Yeah, and all the way to the brain.
Yeah,
Who would have known there was that much detail?
right?
Hope you learned something new today.
I know I sure did.
See you next time.